first things first, let's have a little review. With the table buddy, remind yourselves what is the meaning that we gave to the word derivative and integral. That was the bonus question on the test, so maybe you already went back and looked at your notes to look that up. What would you use a derivative to calculate? That's just more of the same definition. But then, how would you officially calculate 3 plus h squared? So that's a little review of FOIL. So go ahead and calculate that on paper. Just take out a sheet of paper. Honestly, you could just do it all the way at maybe the top of your what does a derivative find. So go ahead and calculate 3 plus h squared. And then what is the shortcut for calculating 3 plus h squared quickly in your head? So go ahead and chat with your neighbor and come to an agreement on those questions. You got 2 minutes. Elias, you came up to now.
Yeah, I can go later actually.
No, that's okay. You went up there. You saw what it is. And Rosa, you came up there too, didn't you? Okay. Well, folks, I hear literally no one speaking to anyone unless you're talking to each other in sign language or some other code. I have missed it. So let's just go ahead and review. What is the meaning of derivative and integral? So what is a derivative? What are we talking about? Yes, we're finding the slope of curvy lines, folks. That's what we're doing for like the next month. We'll be finding the slope of curvy lines. That's what a derivative does. That's what a derivative is. It's the slope of a function at any given point. And what does an integral do? Thank you, Wendy. What does an integral do?
Area.
Yes, the area of a curvy shape, specifically the area under the shape, trapped below the shape, and the x-axis. So that's derivative, that's integral. All of chapter 2 is derivatives. So we'll be finding the slope of curvy lines. And then all of chapter 3 is integrals. And we'll be calculating the area underneath curvy shapes. So what do you use a derivative to calculate? Well, I guess we already kind of said that. We're finding the slope of a non-straight line. So how do you calculate 3 plus h squared? Let me start us off here. What is the first thing you do when you look at 3 plus h squared, Daniel?
You just like put them next to each other.
Yes, put them next to each other. Very good. You absolutely have to write it twice because what is the definition of squared, Monique? Multiply times itself. So you have to do the 3 plus h squared and then write it times itself. Just to clarify, before we even see what the real answer is, it is a common mistake that a student might accidentally just square both of those numbers, right? They might look at that and say, oh, the answer is 9 plus h squared. That's incorrect. It's not 9 plus h squared. But I can, what is that, James? Oh, no, I thought you were contributing.
No,
Okay. So why might someone do that? What does this look like? A valid rule. There is a valid rule that you can do that on. What if you had seen 3h squared? Then what are you allowed to do? Then you can do that. You can actually multiply that power times that power, and you get 3 squared h squared, which would be 9h squared, and that would be perfectly legit. That's correct. That is a correct application when the two terms, well, what's the difference between these? Why are you allowed to do it with 3h, but you're not allowed to do it with 3 plus h? What is it, Daniel?
Like there's 2 terms.
Yeah, these are separate terms separated by plus or minus, whereas this, they're being multiplied. Rosa, is that what you were saying? Yeah. So this is a correct application of the rule. That would be an incorrect application of the rule. And now let's see why. So what process are we about to use, Elias? FOIL. So we're going to go ahead and do FOIL, and I hope you show your work, your arrows. So first, outer, and then inner last. And so that gives us 9 plus 3 times h is 3h, plus h times 3 is still 3h, and then plus h times h is h squared. So after you do FOIL, then what do you do? Actually, Yeah, sorry, combine like terms. So now we really have 9 plus 6h plus h squared. What is the difference between the correct answer and the wrong answer? Because they look somewhat similar.
Trinomial.
Yeah, that's a trinomial, that's a binomial. What else? What specifically is this answer missing? Yeah, the 6h, which was? Yeah, the 2, 3h's, which are the middle terms. This is the OE in FOIL, right? F-O-I-L. This is the OE, the middle terms, and you need those middle terms. This answer right here didn't do the OE. This is not FOIL, this is FLO, right? So that's why this was incorrect, because it didn't do all the steps of FOIL, it just did FL. You need that OE right there. Okay, so now, that's how you officially calculate 3 plus h squared, but how could you just memorize what the answer is? If you saw 3 plus h squared, what could we do to just know what the answer is going to be? 9 is, what relationship does it have to 3? 3 squared. And 6 is doubled. Yeah, 3 times 2. So, yeah, and that would be the rule. It would be the square and then the double, right? So if I gave you all a challenge problem right now of 5 plus h squared, I would like you to be able to FOIL that in your head, like within 1 second flat, and just tell me the answer. So, Luis, what would the answer be of 5 plus h squared?
25.
Yeah.
And 10.
Yeah. Yeah, that would be it. So we'll do this quite a few times over the next class periods. So I don't want us to have to sit there and FOIL that out every single time. The important thing would be able to just know the answer off the top of your head. So here's one more. Let's say you had 9 plus h quantity squared. Karina, what would this one be?
81.
81. You square it, yeah, and then you double it. And then the last term is always h squared. So nice and simple, we can all memorize that. If you want to jot that down at the top of your paper, I think that's a nice idea. We're all going to start on the what does a derivative find packet that you picked up. Rosa.
You don't have to move the terms and stuff like that. You know how it's usually h squared.
Great point. It normally does go in the other order, doesn't it? If you had wanted to, you could have taken the 3 plus h and just written it as h plus 3, in which case it would have been h squared plus 6h plus 9. And you're right. That would be the proper order of the polynomial. Because you're supposed to count down, so that'd be h to the 1, and then this would be h to the 0. And technically, if you were to present your final answer, you'd have to count down from the exponents 2, 1, 0. That is correct, Rosa. However, the work we'll be doing today is going to involve just quite a bit of computations, and this will be in the middle part of the computation. And these terms will either combine or cancel with other terms. And so you don't need to go through the bother of putting them in the right order until you're all done, right? So what we do today, this is going to show up in the middle part of a long chain of steps that we'll do. And so you don't technically have to put them in order. But you're right, Rosa, if that was the final answer, you would have to put them in order. Okay, so that's just our little warm-up. So as far as where we are today, here we are, February 1st. And you'll notice that this first part of chapter 2, so we're just going to do chapter 2.1 through 2.5. That will take February. Bam, February done. Like it will take all the way February 1st to February 27th, because how many days are in February? 28 this year? This is not a leap year, is it? No. So yeah, the entire month of February will be devoted to chapter 2.1 through 2.5, at which point we'll have a review day and then you take your test. Now in this setup, we really will have a review day. So when you come in here on February 22nd, we'll go over the practice test problem by problem. All right. And also note the due dates. The Math AS homework is always due the Tuesday after the week that we did it. So this week, we're just barely starting section 2.1. So you can't see it there, but 2.1 is due on Tuesday on Math AS. All right. Now, Luis came in and asked me a good question in office hours. He said that he wanted to go back and work on a section of Math AS, but it didn't show him his work. So I had to go in and change a setting for him. So please, if any of you have a dilemma with Math AS where you're trying to keep working on a section or you just go to a section to work on it and it won't let you, email me right away so that I can go in and try to fix that for you. Okay? All right, thanks, Luis, for bringing that up. So I'm about halfway done grading all of your tests, so I'll probably finish grading them later today or tomorrow. I'll post the grades online immediately so you can see your grade, and then I'll give you your test back on next Tuesday. All right. Well, the last thing I have to do is tell you an amazing joke. This is one of my all-time favorite jokes. I know you're all going to go tell it to your favorite loved ones. So here it goes. Where, you can barely see it, where does the general keep his armies? Where does the general keep his armies? Don't shout it out if you already know. Where does the general keep his armies? Are you ready? In his sleeveys! Yeah. Where does he keep his armies? In his sleeveys? It's just a really, really silly joke. Probably for children. But I guess that just shows, a little bit more about me. All right, let's do it, folks. Chapter 2 is all about derivatives. And we'll be finding the slope of curvy curves. Now, what do we use the derivative for? I just took this right out of the dictionary, an online dictionary. It says derivative in mathematics is an expression representing the rate of change of a function with respect to an independent variable. So the derivative, really key, is you're going to write both of those things down. Again, just put it up at the top of that paper. What does the derivative find? The derivative finds the slope of the graph, but it also finds the rate of change of a variable. How quickly is that variable changing? Is it changing very quickly, or is it not changing very quickly at all? We will use those words interchangeably. If you say derivative, you could go ahead and just say slope, or you could go ahead and just say rate of change. They all mean the same thing. So I'm going to start us off with the concept of slope, because it's so fundamental. It's key to what calculus is. If you go back, to what, 400 years ago, to the 1600s, when Newton and Leibniz were first starting to invent and write down about calculus, they were really just studying slope problems. They were looking at graphs and saying, well, gosh, what's the slope right there? What's the slope right there? What's the slope right there? They weren't just looking at straight lines. They were looking at curves. And they're like, man, how do I find the slope at any given point? That was the question on their mind. So let's go ahead and fill in some ideas about slope. What's the very first line that I can't see? What does a derivative find? Yeah. Oh, that's the title of the paper. Okay, recall the definition of slope. Slope measures what? What are you measuring when you're looking at a slope? Okay, that's true. You're measuring the rate of change of the graph. But in a simple English word, what are you measuring?
X and Y.
Okay, that's an idea. Angle. You're measuring an angle, kind of, sort of. You are actually measuring an angle. Daniel, what were you saying?
Points on the graph.
Yeah, you're finding points on the graph. What, James? You're definitely finding rise over run. You're finding the slope. So slope measures, one simple English word that you could use is steepness. Steepness. But honestly, everything that you all just said is just fine. Slope measures the steepness. It measures the rate of change. It measures the angle that the particular graph is, on. And slope is always, fundamentally, everyone's favorite F word. Slope is always a
Fun.
fun, yes, and fraction. Yeah, slope is always a fraction. There has to be a numerator and a denominator. So let's take a look at M. Okay, M is just a variable we use to represent slope. M is slope. We're going to define slope in a lot of different ways. So what's the most common way people have defined slope over the years? Yeah, rise or run. Rise or run is always the way they say it. And unfortunately, I think rise and run is a terrible misnomer, because rise makes you think you're always going up, and run, which way are you going? You have no idea. If I just said, run, where would you go? What, are you going to run around in circles? You're going to run to the right? You're going to run to the left? It's terrible. So rise or run is not the best word to represent slope. Instead, my definition that I'll use throughout the class is the up, down, over the right, left. And I always say it with an accent because I think it's fun. So that's the up, down, the top number, the numerator. It tells you if you're going up or down. Of course, if the number is positive, you're going up. And if the number is negative, you're going down, because that's what a graph is. If you look at a graph of the x, y axis, up is positive, down is negative on the y-axis. And if you go right, it's positive. And if you go left, it's negative. All right. But calculus goes a little further with that, and they just want symbols. Instead of saying the up, down, or the right, left, they might just say vertical change over horizontal change. right? A little more professional. What is your vertical change? You know, how far up or down did you go? What is your horizontal change? How far right or left did you go? Calculus takes it even further than that, and they do a symbol called delta y, delta x. That symbol is called delta. I think it's the Greek alphabet letter D, D for delta. And D, what do you think D stands for? Derivative. Well, yeah, kind of. It could stand for derivative because another way that we do that is dy dx. And that's also still standing for delta, which means change it, okay? Delta technically means change it. So if you want to make a little note there, D or delta means change in. All right? So absolutely everything that you're looking at right there is referring to slope. And while we're at it, we might as well throw in the very last term, which we started on the first day of class, f prime of x. F prime of x is referring to the slope of that function. So don't mean to overwhelm you here, but all those symbols mean the same thing. And that way we know right up front that all these symbols are synonymous. They're all referring to the same thing. Okay, slightly easier question. What are the 4 types of slope? Slope could be positive. Slope could be negative. Slope could be 0, or slope could be undefined. Now, right now, if somebody walked up to you off the street and they said, why do we say that this one's 0? And why do we say that this one's undefined? Couldn't we have done those backwards? Couldn't we have said that one was undefined and that one was 0? Why is it that this one is 0 and that one's undefined? What would you tell them?
That's not math.
Okay, yeah, you could say that. That's how math works. Get out of my face.
Can we get an chapter 2?
Oh, you didn't get it?
Yeah.
Oh, you poor thing. Here's one of each. There you go.
Thank you.
Well, we're going to be able to answer that question in a moment. Now, when we talk about slope, all right, let's go ahead and take a look at some of these. What do larger numbers represent? Like, let's say that I had positive 10 over 1. What does a large slope represent? What would you say about a line whose slope is a large number? And everybody watch, I'm going to show you. Well, first of all, how do I read that in English? In up, down, right, left?
Up 10.
Up 10, right 1. So everybody watch my fingers, okay? Up 10, right 1. Up 10, right 1. Up 10, right 1. Up 10, right 1. What would you say about that line? Oh, yeah, it certainly is straight. And it's fairly steep, right? I mean, you wouldn't want to walk up that. That's like climbing. So a large number is steep, right? And I'm just saying 10 is a large number. Whereas, what if I had a smaller slope? You know, I won't even give the example of up 1, right 1, because that one's fairly clear. Up 1, right 1 is a diagonal. It's a perfect diagonal. But what if it's a small number like a fraction? What about 1 over 10? What does a small fraction represent? And again, you can watch my fingers as I do it. I'm facing you, by the way. So up 1, right 10. Up 1, right 10. Up 1, right 10. What does that line look like? It's not very steep. What English word did you use besides, you know, to be the opposite of steep? Yeah, somebody said it, what? Shallow. It's a fairly shallow slope. One of my favorite shallow slopes is when I drive out of Phoenix and I'm going up a mountain or down a mountain, and you guys have all seen these yellow signs where there's something like that, and it does something like this.
6%.
You guys all seen that?
Yeah.
Yeah, so that means you've got a 6% grade. What does that mean? 6% steepness, what does that technically mean? First of all, fairly shallow still, right? I mean, 6% is fairly shallow. You know, your car can't drive up something like this. So, I mean, it's still fairly shallow. But what does percent mean? Literally, the etymology in Latin, per cent. What does cent mean? What is it?
100.
100, yeah. Everybody's cent means 100, right? Because there's 100 cents in a dollar. A century is how many years? 100. So cent means 100. So guess what? 6% literally means 6 per 100. That's literally what it means, 6 per 100. And that's a slope. What's the slope say? In the up, down, right, left. Up 6, right 100. Up 6, right 100. So that's literally what they're telling you about the road when you're driving up or down the road.
700 feet. So you go,
Yeah,
you go
yeah,
6
for-
feet higher.
You go 6 feet higher for every 100 feet you go to the right. Yep, absolutely. That's what that means. So that sign is actually a slope. It says a percent, but it's really a slope. Okay, well, dandy. So those are larger numbers, smaller numbers. Next, recall the formula for calculating slope when you have 2 points. So I went ahead and just told you the formula. I mean, you all know the formula. Do you have to write it as y1 minus y2, x1 minus x2? What else could you do?
y1 or y2 minus y1.
Yeah, so you could do that as well. What you can't do is 2 minus 1, 1 minus 2. That would get the numbers mixed up and you wouldn't get the right answer. You have to be consistent, 1 minus 2 or 2 minus 1. Okay, so that's the slope formula. Let's go ahead and do one calculation together of an actual slope in terms of reading it. So we want to find the slope between -2,4 and 3,1. My personal preference is I do everything visually first. So on your graph, go ahead and put the coordinate -2, 4, and then put the coordinate 3, -1. And then you can go ahead and draw a little line there connecting them. So first of all, is the slope positive or negative? Negative, so we already know the answer should be negative. And is it steep or shallow? It's kind of in between the two. It's not exactly steep, it's not exactly shallow. So on your graph, go ahead and show me the delta. The delta means how far, oh, so first of all, folks, we always start on the left and we move to the right. Why do we start on the left and move to the right? What would be a good reason why we start on the left and move to the right? That's how we read and do everything in our culture. Everything goes from left to right, right? So starting at this point, I would do my vertical change first. What is it? We go down, is it down 5? Yeah. And then I go to the right, and that was right. Oh, also 5. Okay, now everyone do this with me. Using the definition of m without the formula, m, right, is up, down, or the right, left, which is also known as the delta y over the delta x. Let's get used to this calculus terminology. What was the delta y? The delta y was -5. That was your change in vertical placement. So our delta y is -5. And what's our delta x? Positive 5. So that was our delta y over delta x. And so the answer is just what? Down 1, right 1. So in fact, that was neither steep nor shallow. That was right in the middle between, steepness and shallowness. All right, now let's do the actual slope formula. Folks, when you write the slope formula, please do this with me. First, always write down the formula, y2 minus y1, x2 minus x1. Then write the formula empty by just writing a fraction line and 2 minus signs. So now we just have to plug in our numbers. So let's go back up to the numbers that we were given and go ahead and label it. That's our x1, y1, and then that's our x2, y2. And go ahead and just plug in those numbers and then calculate them. In fact, you might have already done it. You guys are speedy. You're probably not shocked by the result. In fact, Karina, what was the literal result? What did you get it equal to?
So -1.
Oh, the first thing you wrote down.
Oh, -5 over 5.
Yeah, it literally gave us the exact same thing we saw visually. I suppose I should plug in my numbers. So it's -1 and 4, and 3 and -2. Right, and then it, of course, simplified to the same results. Okay, so in this class, we'll be doing both. We'll do it visually, we'll do it with the slope formula. Feel free to be flexible and go back and forth between the two. The key is we want to be able to read it. Okay, turn the page. So what we have here is just a graph. This is a very common thing that we'll do, is simply look at a graph and describe it. How would you describe this graph? Like, again, somebody walks in off the street, they can't see the board because they're blind or they're blindfolded, who knows? And they say, oh, what does the graph on the board look like? What would you say to them? Rosa, what would you say to them? The graph?
Steep.
And then? What happens at the top?
It stays.
Yeah, it flattens out. And then?
Decreasing.
Decreasing for a while, and then? Yeah, it stops for a second, it's flat, and then? It goes back up again, right? If you were just to use really common, simple English, you'd probably tell someone, yeah, the graph starts at -1, it goes up for a while, then it reaches a maximum, then it goes down for a while, and then it reaches a minimum, and then it goes back up again, right? You just describe it. What I'd like to do is label a variety of points on this curve with reasonable values of slope. So for instance, out of all the points that are on that curve, what are the 2 points that we know for sure we can nail the actual value of the slope? You're thinking maybe this one because it's up one, right one? Is that what you said? Oh.
So, 1 and 2.
Oh, you mean this point? And this point?
Mm-hmm.
Yeah, why is that? What's the slope here? What's the slope right up there at the top, folks? 0. So go ahead. Right above it, just write m equals 0. We know for sure that right there, that slope is 0. And in fact, everybody, right there at that dot, go ahead and just draw like a little line there. It's just a little line. It's a slope line. It says right there at that point on the curve, if I were to draw a line tangent to the curve, that's what it would look like, and it'd be perfectly flat. And then likewise for this one. What's the slope all the way at the bottom, Wendy? Yeah, also 0. So right down near the bottom, I'm just going to draw a short little line, and that little line is just like a level. You know, like a level. If you're at Home Depot and you're checking to see if it was level or not, your level would touch right up against the line, and you'd have an m of 0. Okay, so those two we know for sure. What about this slope? What would you say the value of that slope is? Definitely positive, right? Let's say that. So right here, if I were to draw my little slope line, I would say definitely it's a positive slope. Anyone just want to take a guess as far as steepness goes?
1.
I think 1/1 is a pretty good guess. That right there at that point, you're going, you know, up 1, right 1, up 1, right 1. It looks like the perfect diagonal. So I'm going to go ahead and call that one up 1, right 1. Now, did we actually calculate that answer? No, so we have no idea. Well, let's keep going. What would this slope be?
Maybe -1.
Definitely negative something. It could be 1/1 again. Maybe that one is the perfect diagonal. Remember, when I'm talking about a perfect diagonal, I'm talking about an isosceles triangle where the diagonal is exactly 45 degrees and 45 degrees. That would be down 1, right 1, right? So yeah, let's go ahead and call that one down 1, right 1. Then what would this one be? It's a little steeper. That means you're going down more with every unit to the right. So what might that one be? Yeah, maybe down 2, right 1. So that slope would be down 2, right 1. What would this slope be? A little steeper yet. What would it be? Let's see here. Monique, what do you think about this one? Yeah, maybe down 3, right 1. You know, we're not actually doing calculations, so we can't say for sure. We're just trying to give relatively correct values. And then what about this slope? Right there. It's right before you hit 0. Yeah, maybe, what kind of half? Still negative, right?
Yeah.
Yeah, good, maybe 1/2. You know, it's going down 1, right 2. Down 1, right 2. So it's not as steep as those other ones. Okay, so folks, historically speaking, we were just in the shoes of Newton and Leibniz. So just to make sure everybody knows how to spell that, Newton and Leibniz. You know, they were the two mathematicians in the 1600s who wrote about calculus first. They did it within years of each other. There was a big battle as to who actually invented it and who should get the credit. I think nowadays everybody agrees that they both contributed to the birth of calculus, but they've definitely fought each other. Like, I invented calculus. No, I invented calculus. So this is what they were trying to think about. They're like, man, yeah, sure, I'm looking at this curve. I can kind of guesstimate, but how do I know for sure? How do I know for sure what the actual slope is at these points? And that's the problem they were trying to solve. So taking a look at one more graph down here. This one, we can do the same thing, right? Go ahead and attach some slope values. I'm just going to call around the room. You just need to give me a relatively correct slope. So what would this slope be, Elias? And always start your answer with positive or negative. Yeah.
2/1.
Positive 1/1?
Yeah, sure.
What did you say?
As a 2/1.
Oh, 2/1. Okay, it could be 2/1. Yeah, but positive 2/1. Okay, what about this one? This one, Luis, what do you say? More or less steep?
More.
More steep, so the slope could be
1.
well, this one is already, he claimed that it was up 2, right 1. So you'd have to be even steeper than 2. Yeah, maybe 4. Maybe up 4, right 1. Okay, now what about this one? It's kind of tough to tell. You could argue probably two ways on it. James, but what do you think? What's the slope right there?
Almost like 0.
Yeah, it almost looks 0. I mean, if it wasn't 0, it would be the most gradual upward slope you can imagine. Like up 1, right 100. Or, that would be like a 1% grade, right? On a road, 1% grade. So maybe you could claim that this is more like up 1, right 100. But I mean, what's 100th? 100th is awfully close to 0, isn't it? 100th is like 0.01. Okay, now what about this one? What could that one be, Anna?
I feel like the same.
Yeah, I mean, it could still be 0. It could still be slightly. Do you think it's slightly up or slightly down? If you had to choose.
Down.
Slightly down. Yeah. So I mean, who knows? Okay. What about this one? Ashley, what would you assign as a slope value for this one? Oh, I like it. Yeah, -5/1. It's fairly steep, so you'd be going down 5, right 1, down 5, right 1. All right, very good, folks. Now, let's just consider this graph was different from the last one because it has units. This graph actually has units. So let's just take one of these slope values. I'm going to take the positive one right here. This one that said m equals 4/1. For what? 1 what? 4 what?
4 feet.
Is it 4 feet or is it 4 seconds?
4 seconds? No.
4 feet.
How do we know for sure? What's the definition of slope?
Up, down.
Yeah, the up, down, and the right, left. Delta y over delta x. So y is telling us what unit to look at. It's for what?
4 seconds.
4 feet.
4 feet for sure. Yeah, because that's the delta y. Yeah, so that's really 4 feet, and then what? Oops, feet over 1 second. So what are we really saying when we say 4 feet per second? Are we describing a distance, a time, or something else? If you say 4 feet per second, what are you really describing?
How much feet you go per second?
Right, which is a description of. Like right now I'm going 4 feet per second. Right now I'm only going 1 foot per second. Yeah, speed, right? So what this slope is actually describing is speed. Notice how fun this is. The y-axis is describing distance. The x-axis is representing time. And the slope is representing rate of change, speed. And where have we seen the letters distance, rate, and time? What's the formula? D equals?
Rate.
Yeah, D equals RT, right? That's just the classic formula for distance equals rate times time. So this is pretty cool, that when you're looking at a graph, you might think you can only talk about distance, which is the literal distance up and down the y-axis, or you could be talking about time, which is the literal distance along the time axis. But if you calculate the slope of the graph, you can actually be talking about speed as well. So slope really truly gives us new information. If all you had was a bunch of data about your distance and your time, you automatically now have data about your speed as well by simply calculating the slope. So it's pretty powerful. Okay, so how can you approximate the velocity of a moving object by looking at a distance versus time graph? How do you find their speed or their velocity? You would calculate the rate or the slope, right? Find the slope. So just to make sure that we're all appreciating what we're doing for the whole next month of February, we're calculating slopes, we're calculating rates of change, but also if our graph happens to represent something in physics, like a distance versus time graph, you're actually calculating the slope on purpose in order to calculate the velocity of the moving object. Okay, now down here at the bottom, folks, I just included, it's not on your paper, but I included a screenshot from your textbook. So for instance, just to throw this out there, I assume that you all read the textbook section 2.1 before coming to class today.
Yeah.
Right, that is my assumption. That before you come to class, you read the section in the book that we're about to do. If you did do that before you came to class today, fantastic. If you did not, do it next time. Next time we're meeting to talk about section 2.2, I assume you will have all read 2.2 before coming to class. Hence, this little picture should be familiar to you because it was in section 2.1. And what did they say about average velocity? It's your delta position, which is your distance, where are you, over your delta time, which is your change in time. So that's the definition they gave us, is that by calculating a slope, you're calculating an average velocity. Now they also said, though, an instantaneous velocity is the actual slope of the line tangent to the graph. So we want to kind of start distinguishing between these two things, average velocity and instantaneous velocity. So on your graph, you might already have something written there, but let's just do this. If I were to choose this point and this point, I could find my average velocity. All right, that's called a secant line. A secant line is between any 2 points. So pick 2 points, folks, and call that your secant line. If I were to calculate the slope of that line, that would tell me the average velocity. Okay, we're talking about speed or velocity. The slope of that line would tell me the average velocity over the time interval from, let's say, 12 seconds to 20 seconds, right? So if you calculate a secant slope, the slope of a secant line that goes through 2 points, the slope of that line is actually the speed, your average speed, over the whole interval of 12 to 20 seconds. So from t equals 12 to t equals 20, what was your average speed? The slope of that secant line. Whereas, all right, whereas if I chose exactly just 1 point on the graph, just one, and I draw a line tangent to the graph. Do you know what tangent means? Tangent means that you just barely touch. Tangent is touch. It means you just barely touch. So now if I choose this tangent line, then I'm literally finding the velocity of this vehicle at exactly time equals 26, right? The tangent slope, which only touches at 1 point, then I'm literally, if I can find that slope, it's literally the speed of the vehicle at precisely 26 seconds into the journey. So a tangent slope tells you the instantaneous velocity, much like if you looked at your speedometer. How fast are you going right now? Whereas a secant line is telling you the average velocity between any 2 points. Between time 12 and 20, I was going an average of that velocity. Okay, we'll certainly talk more about this, but those are some nice ideas from this graph. Okay, you know what? I also pulled this out of the textbook, but I don't think we really need that right now. So I'm just gonna keep on going. Okay, goody gumdrops. Go ahead and turn the page. What we're about to do is reinvent the wheel. We're about to recreate the discovery of calculus by Newton and Leibniz. That's what we're about to do. We're about to go through the thought process of what they did when they were inventing calculus, okay? So everyone, right now, would you rather be Newton or Leibniz? Are you a team Newton or are you team Leibniz? Luis, who are you? Adam?
Oh, yes.
Newton? Oh, Newton? Newton? Go with Leibniz. Newton? Leibniz? Newton? Newton? Leibniz? Okay, Newton. Okay. So you're choosing one person who you're really enjoying. The great news is Newton and Leibniz were both doing this. Okay, they were at their separate homes, hundreds of miles apart, but they were both thinking about this process that we're about to do. So let's just all pretend that we're back in the 1600s and we're about to do what they did. So let's start on the top line. I can't even see it. The aim of differential calculus is to find the slope of what? Of a curve at 1 point. 1 point. We want to find the slope of a curve at a single point. That would be the tangent, right? Like if I've got this curve right here and I want to find the slope at 1 point, okay? The slope at 1 point. That's what we're trying to do. That's what calculus is trying to do. And what kind of a line is that called again? Tangent or secant? It's tangent. So that's the goal of calculus. That's the goal of differential calculus. Find the slope at a single point. And so in order to use the slope formula, what do you need though? To do the slope formula, how many points do you need? Technically you need 2 points. Right? So already you can see the dilemma. X1, Y1, X2, Y2. Here we are, wanting to find the slope at a single point, and yet the only slope formula we have, you need 2 points. Right? What is that, like a paradox? A contradiction? We're stuck? What do? You want to find the slope at a single point, But the only tool you have for calculating a slope requires 2 points. So what do? You need 2 points, but you only want to find the slope at a single point. Right? So this is the fundamental paradox that they face. How do I do this? Differential calculus finds the slope between 2 points that are, ready for it, infinitely close. Okay, so they cheated. Newton and Leibniz, they're like, hey, I want to find the slope at that point. So what they did was they said, well, what if I just choose another point? Okay, that way I can use the slope formula and find the slope between them. And then you know what they did with the second point? They just started moving it closer and closer and closer until the point was infinitely close. And then it's like, whammo, you did it. You do have 2 points, but how close are they? Infinitely close. So it's kind of like they're just 1 point, right? So you see how they cheated? This is the fundamental method of calculus. You cheat. You want to find the slope at 1 point, so you make up a second point, and you bring that point infinitely close, because then technically you have 2 points. But technically the distance between them is 0, because they're infinitely close. So that's our methodology. So the method: find the slope between a given point, okay, the given point that you actually want to know about, okay? So there is a point that you actually want to know. Hey, what's the slope at that point? So you find the slope between the given point and another point near, well, infinitely close. So this is fun. This is what we're about to do. So let's take a look here. At the very top of the paper, I gave us the goal. Find the slope of the curve at the point x equals 1. So everyone, on your x-axis, go to the point 1. I'm just going to go and label it real quick. Put a dot on the graph right there. That's the point we're actually interested in. And then make a teeny tiny little slope line. And by slope line, I mean a little line that's tangent to the curve. So that little teeny slope line right there, I am pretending, you know, that it's touching the curve at exactly 1 point, and it truly represents the actual slope of the tangent. So first of all, what is the slope, positive or negative? Shallow or steep? Really shallow, right? So now all we have to do is just nail down the precise value. So here we go. What we'll do is, again, we'll pretend that we're Newton and Leibniz, and I want to choose a point to the right. Now, where do I actually want to choose my point? Infinitely close. But just for now, let's go ahead and choose a point far, far away at 3. Okay? We're like warming up. I'm going to choose 2 points that actually are a bit of a distance away from each other. So let's go ahead and find the distance, or sorry, the slope between 1, 1 and 3, 9. Now while you're at it, folks, go ahead and draw a nice tangent, not tangent, secant line. Draw a secant line. You probably need like a credit card, or you can use your book or something to draw a nice straight line. I apparently do not have a straight edge anywhere nearby. I will draw this. The key thing is that I want you all to notice that what we're about to do is calculate a secant slope. Right? There we go. Yeah, so we're about to calculate a secant slope between that coordinate and this coordinate. Now, by the way, folks, what is that coordinate? All we've said so far is the x coordinate. What's the y coordinate? What graph is this even of? Did we say? Did I say? No. I apologize. This is the function of a parabola, a simple parabola. It's just x squared. That's it. So if my input is 1, what's my output? 1. Because you just square it, right? 1 squared is 1. So the actual coordinate is 1, 1. What about what's my actual coordinate over here at 3? Yeah, 3, 9, right? Because you just plug 3 into x squared. 3 squared is 9. So that's the actual coordinate. So now let's go ahead and find the slope between 3, 9 and 1, 1. And I want us to be fast about this. So everyone, I'm going to show you a great shortcut here for finding the slope between 1, 1 and 3, 9. I draw little arrows. So I say I'm going to do y2 minus y1. So I connect my y coordinates with a line on top, and I'm going to subtract 9 minus 1 on top of my fraction. Right, so I just technically did y2 minus y1, and then I'll draw a line on bottom connecting my x coordinates, and I'll do x2 minus x1, 3 minus 1. And so my answer is 8 over 2, which is 4 over 1, which is really just 4. But 4 over 1 is the better answer because it's a slope. Okay, so what was the slope of this secant curve? 4 over 1. What's the actual tangent slope supposed to be? A little shallower, right? The real tangent slope that I want is actually shallower than that. So is the value of 4 too big or too small? Too big, right? So let's go again. Using the method of Newton and Leibniz, let's choose a point a little closer, and let's slide this point a little closer, and we'll do 2. So now let's calculate the slope between 1 and 2. We're in the process of moving the point infinitely close. We're just doing it slowly. So once again, I'm going to draw my secant line. Now I'm calculating the slope between 1 and 2. And you'll notice for the secant slope now, is it the same slope as the first one, or steeper or shallower? It's a little shallower. And in fact, it's a little closer to the slope we actually want to know, which is tangent at 1. So now we go ahead and calculate the slope between, what's that coordinate, by the way? It's the coordinate 2 what? 2, 4. Because how do you calculate y coordinates? You just plug the x coordinate into the function, so 2 squared is 4. So that's the coordinate 2, 4. So everybody try the arrow method and go ahead and calculate the slope from 1, 1 to 2, 4. So 4 minus 1 on top, and 2 minus 1 on bottom. And what's our slope now? 3 over 1. Oh, well, that's good. It got a little shallower. You know, it's slowly but surely we're going to start approaching our actual tangent slope that we're interested in. We're just moving there a little bit at a time. So we started arbitrarily at the point 3. We slid it closer to 2. Let's slide it closer again. And we're going to slide our point close to 1.5. So now we're at this point, 1.5. And now we're going to calculate the secant slope between 1 and 1.5. So I'm going to draw my secant slope again. Can everyone tell that my secant slopes are getting shallower and shallower? And that they are theoretically approaching the tangent slope that we're interested in? So what's our coordinate now? 1.5 comma what? Again, you take your x coordinate, plug it into the function. So what's 1.5 squared? What is it, Ashley? Yeah, 2.25. So now let's go ahead and calculate our slope between 1, 1 and 1.5 and 2, 2.25. So again, drawing your little arrows, 2.25 minus 1 is 1.25. And 1.5 minus 1 is 0.5. And on your calculator, what is 1.25 divided by 0.5? It is? What's 1.25 divided by 0.5? 2 what? Yeah, 2.5 over 1. So notice, folks, our slope values. We've gone from 4 over 1 to 3 over 1 to 2.5 over 1. Our secant lines are sure enough, they're getting closer and closer and closer to the tangent slope that we're interested in. Now, we want to go ahead and keep sliding that point closer. We're just going to do it one more time. We'll do 1.1. So slide that point a little closer. And by the way, folks, how close are our points now? They're pretty close. Yeah, they're super close. What's the distance between them? Between 1 and 1.1? Well, the distance between them, we can just look. The distance from 1 to 1.1? It's just 0.1. So these points are pretty close. Are they infinitely close? No, not yet. I mean, they're 0.1 units away from each other. But no, they're not infinitely close. But this is the process that Newton and Leibniz did. They just bring it closer and closer and closer and closer. And they trusted that these numbers are going to start approaching one particular value that would be obvious. So let's go ahead and slide it to 1.1. What's that coordinate now? 1.1 comma what? What's 1.1 plugged into x squared? All of you should be typing this into your calculator to find out because you're on the edge of your seat. Ooh boy, what is 1.1 squared? What is it? 1.21. All right, so now let's calculate that slope. So our slope is 1.21 minus 1, which is 0.21, and then 1.1 minus 1, which is 0.1. And what is 0.21 divided by 0.1? 2.1. Okay, folks, do you think you see what number we're approaching? What would be your guess? We went from 4, 3, 2.5, 2.1 to probably we're approaching 1. And without drawing another point, because we really can't do much more drawing in there, let's just go ahead and pretend we did the slope between 1 and 1.01. What would that slope be? I already plugged in the points there. So that'd be 1.0201 minus 1, which is 0.0201, over 1.01 minus 1, which is 0.01. And what's 0.0201 divided by 0.01? 2.01. So do we all feel pretty sure that if we continue to slide this point infinitely close, what will our ultimate slope be? What would our ultimate slope be? What is this number approaching? 2. Yeah, we're getting closer and closer to 2. If we kept getting closer and closer, if we brought our points infinitely close, the answer would theoretically be 2. So let's go ahead and turn the page, and let's do that. We're going to now actually slide the points infinitely close. And if we do slide the point infinitely close, then in theory, we just found the slope between 2 points that are infinitely close, which is the same as finding the slope at a single point. Right? That's the philosophy. You have to agree that 2 points that are infinitely close is the same as 1 point. There's still technically 2 points, but we're agreeing philosophically that it's just 1 point. So here's what we're going to do. You'll notice it's the same graph, right? Find the slope of y equals x squared, that's the function, at the point 1. So go ahead, everybody, and mark that point again. There's our point 1, 1. And what we want to do is choose another point over here, but we don't want to say how much further to the right it is. I'm just going to say that I'm starting at 1, and I'm going to choose a point that is h units to the right of 1. So what coordinate would that be if it's h units to the right of 1? That would be the coordinate 1 plus h. Now that might feel crazy, but remember a second ago we chose the point 3. That was 1 plus 2, so that was 2 units to the right of 1. And then we chose the coordinate 2, that was 1 unit to the right of 1. And then we chose the coordinate 1.5, that was 0.5 units to the right of 1. So I just don't want to specify how many units to the right of 1 I am, so we're just going to use the letter h. So I'm h units to the right of 1. Okay, so what's that coordinate? We know that the x value of the coordinate is 1 plus h. What's the y value of the coordinate? Since our function is x squared. This hurts the brain just a little bit, because you might feel unsure about what to do. If I told you that the x coordinate was 5, what would you do with your 5? You'd square it. If I told you the x coordinate was 4, what would you do with the 4? You square it. If I told you the x coordinate was 3, what would you do with it? Square it. I'm telling you it's 1 plus h, so you square it. So it's 1 plus h squared. That's the coordinate. Now I know that looks very abstract, but saying that the coordinate is 1 plus h comma 1 plus h squared. But I just want you to notice that as soon as I tell you a value of h, it would tell you a coordinate. Like for instance, let's just go ahead and say that my h value is 4. I'm going to go 4 units to the right of 1. Okay? So I'm going to take my formula here, 1 plus h and 1 plus h squared. And I'm going to tell you, let h equal 4. Now, if h is 4, what does that mean? 1 plus 4, I'd be at the coordinate 5. And what would the y value be? Well, 25, right? 5 squared is 25. So if I let h equal 4, 1 plus 4, comma, 1 plus 4 squared, and what's the result? 5. 5 squared, 25. So the formula works. The formula works. All you got to do is tell me the value of h to plug in there, and it will tell you the coordinate of whatever h value you set. The thing is, we just don't want to say what our h is. We want to do it in general. So now we're prepared to say, challenge, find the slope of y equals x squared at the point 1. Method, find slope between x equals 1, and a point h units to the right. Okay? Now you all have plenty of room now down below that, right? There's a huge blank space. And in that blank space, we are going to calculate the slope between the coordinate 1, 1 and the coordinate 1 plus h squared. So here's what I'm going to do. You can follow along with me. My first coordinate is 1, 1. That's my x1, y1. And my second coordinate is 1 plus h squared. And that's my x2, y2. I strongly recommend you write down everything I'm about to write down right here, because this is the thought process. These are my 2 points in space, and I'd like to calculate the slope between them. You guys all have like goosebumps of excitement because we're doing what Newton and Leibniz did 400 years ago? Yes, yes, I totally do. I knew it. I knew it. Okay, so first we write down the slope formula. M equals y2 minus y1 over x2 minus x1 equals long line with 2 minuses. All right, so there's our slope formula. I write it empty with the long fraction line and 2 minuses, top and bottom. Now what should we do? Just plug them all in, right? What's my y2?
1 plus h squared.
Yeah, 1 plus h quantity squared. What's my y1?
1.
1. What's my x2?
1.
And what's my x1? Now, how does everyone feel about that? You might still feel a little uncomfortable about this h business, but just remember, if someone says, what's h? H is how many units you are to the right of 1. Right? It could be any number you like. So now what do we do? Everybody, off the top of your head, what is 1 plus h quantity squared? And we can write it down in any order we like, but remember, it was square it and then double it. So 1 squared is
1
plus
1 doubled is 2h, and then plus h squared, and then minus the 1. And on bottom, well, what can we do on bottom?
Just h.
Yeah, because we can cancel out those 1s. And in fact, something really exciting is that when you do calculus, it ultimately is just lots and lots of algebra and lots of cancellations. So we just did our first cancellation. Where can we do our second cancellation? Yeah, but the top, cancel out that 1 and 1. And what do we have now? 2h plus h squared all over h. Now I'm sure you're all dying to do what? Cancel out an h, right? Now we have to make sure we do it properly. We're going to factor an h out of the numerator. We factor an h out. So if you factor an h out of both of those terms, what's left inside?
2.
Yeah, 2 plus h. And then what happens with the h on bottom? They clearly cancel out. Right? How many cancellations did we do total?
3.
Yeah, 3 total. Calculus is lots of algebra with lots of cancellations. Okay, so we ended up with this. Let's rewrite. M equals, what's the slope between those 2 points? 2 plus h. For any h value you choose, to pick a point over here that you want to find the slope between them. Whatever h value you choose, the formula for the slope was 2 plus h. And is that correct? Flip it back over on the other side and look at your answers. When we found the slope between 1 and 3, what was the slope? Wait, did we start at 4? Or did we start at 3? What was our first point that we chose?
3, 9.
Yeah, we did 3, 9 first. What was the slope between 1, 1 and 3, 9? 4, right? 4. What's the distance between 1 and 3?
2.
2. And so if we plug in 2 into this formula, 2 plus 2 is?
4.
4, which is the slope we said it was. What about the other point we chose? We chose 1 and 2. What was the slope between 1 and 2?
4.
The slope between the coordinate 1, 1, and 2, 4. The slope was 3. And what's the distance from 1 to 2? H equals 1. And so 2 plus 1 is 3. So this formula really is giving us all the values that we just had a second ago. So here's the exciting part. Where do I want to choose my second point? I don't want to choose my second point way over here. Where do I want to choose it? Infinitely close. And if 2 points are infinitely close, what's the distance h between them? 0.0000001? 0.00001? Or essentially 0. So here's what we write now, folks. This is your first piece of calculus. We take the limit as h approaches 0 of the expression 2 plus h. Now, this word limit here means let h become as close to 0 as you wish. Allow that h value to become 0.0000000000001, and even smaller than that. And essentially, that means we can just let h equal 0. And what happens if we let h equal 0 in this expression? The answer is 2. And that was the slope we suspected. We suspected that the actual slope at the point 1, go back now and put your little tangent line there. What's the actual slope right there? The slope is 2. Sure enough, it is 2. This is the result that we get from calculus, is that we wanted to find the slope at 1. We chose a point arbitrarily to the right, h units to the right, calculated the secant slope between them, and then we allowed that h value to shrink away to nothing. And then that secant line became the tangent line. So that's our first calculus result. We just did what Newton and Leibniz did. And so the slope at 1 truly is 2 over 1. Okay, let's just answer this question. Distinguish between average velocity and instantaneous velocity. Instantaneous velocity, again, if this curve represented like distance and time, the instantaneous velocity is the tangent curve. That's the tangent curve, the actual speed at that actual moment, right? In other words, that's your speedometer. If you look at your speedometer in your car, is your speedometer telling you the speed you're going right then? Or is it telling you the average speed of your total trip? Yeah, that's crazy. Your speedometer does not tell you on average how fast you've been going for the last hour. It tells you how fast you're going right now. And that's instantaneous velocity. That's the tangent slope. Whereas what's average velocity? That's the slope between 2 points. That's your secant slope. And again, that's just your average velocity. One more thing to add to this. Average velocity, you always need 2 points. It's the slope between 2 points. Whereas instantaneous velocity, your tangent slope, that's the slope where? At one single point. So if somebody asked you on the street, they said, hey, what is the first calculus result that Newton and Leibniz gave us? The answer would be, a what? Yeah, instantaneous velocity. The answer would be the ability to calculate slope at a single point. That's the first thing they did. The ability to calculate slope at a single point, which again should be surprising because the slope formula requires 2 points. Okay, dandy. So let's just see here. I think, yeah, I said skip for now, but keep it. So we're done with this packet for now. And when you get back from your break, we're going to start on the Math AS homework for 2.1. Essentially, I took Math AS 2.1, I printed up all the problems from it so that we can look at the trickier ones together. And that way, when you go home tonight, you'll be able to have some notes about how to do the problems. But it definitely is break time. It's 12:05. Everybody is back in the room at 12:15.
What's that?
It's really fun.
Ah.
Yeah. I don't know about another one because my friends if you buy something for school and you put in your taxes, they can be free.
Yeah.
Yeah. So I'm probably fine with it. Honestly.
Cause I have like a desktop, but I want a small one for like college, you know, something like.
Si es tan grande, yo quisiera like una like 14.
Una chiquita. Sí, yo también quiero una chiquita. Pero que tenga de 10K.
¿O esto?
Mhm.
Oh, no, esto no creo que más salen los grandes.
Yeah.
I think so.
Porque una muchacha me estaba diciendo que iba a hablar una, pero no sé qué ya era. Pero que quiero después.
Yeah, really useful.
I love how you're switching back between Spanish and English.
Oh.
A second, I heard you talking to him in English, and then he said pero, and then he said more. And I was like, did you just switch to Spanish? And then you said,
Yeah, this is the.
and then he said, sí, yo quiero because. And I'm like, man, this is fun. You're just going back and forth. I love it. That's so much fun. I honestly kind of do that with my wife because she speaks fluent Spanish and I only speak a little Spanish. So if I'm talking to her, I try to speak in Spanish until I get to a word I don't know, and then I just say it in English, unabashedly.
I don't know. My son, he's 2. No, he turned 3. So he knows both, but sometimes like stuff that he doesn't know in English, he tells me in Spanish. So then I tell him so he can know like how to say it.
Yeah, sure.
But we were going to therapy and stuff, and they told me that he was learning pretty fast both languages. Like,
Oh yeah.
they're small, you know, so they get to pick up faster than us.
Yeah, absolutely. All right. One more minute. Rosa, I wonder if that happens in math. Like you're solving a math problem, and then you just keep switching from fraction to decimal, just like whatever's more convenient at the moment. That'd be pretty interesting. Because normally people would just stick with one way, like fraction, or decimal.
I think nobody likes fractions or fractals.
All right. Folks, we're going to switch our attention now to the packets that I gave you. Now, this is probably what I will often do, is that on the one hand, I'm going to have, oh wait, that's good. On the one hand, I will have a notes packet for you. Oh, is it here? Oh, yeah, I'm so sorry. I'm just throwing your stuff everywhere. Okay, so what we just did this morning so far was I introduced some ideas and gave us an overview, kind of a historical look, and like an exercise. But then this is the actual homework packet. So when it comes time for our next test, this is the one that I'm actually collecting for a grade. I want to see that you did every single problem on this thing, and then that's what you'll do for a grade. So this other one, what do we find with the derivative, everything we just did? I'm not collecting that for a grade. That's just for your own, experience in life. Whereas now this is for a grade. That's not to say you shouldn't take those other notes. You should definitely take those other notes as providing key ideas. But this one happens to be for a grade. So here we go, folks. Use the graph of f to evaluate the average rate of change from 2 to 4. Now again, probably wouldn't hurt if we had these definitions handy nearby. What does average rate of change mean? Average rate of change is referring to what?
The secant.
Yeah. Yeah, exactly. Secant, both of those are correct. Thank you, Rosa and James. Secant slope and the slope of 2 points. Right? That's the average rate of change. Whereas instantaneous rate of change is referring to the what? Yeah, the tangent slope at 1 point. Again, we can very easily look at these two things and call them something. This one, pre-calculus. This one, calculus. So, what's the average rate of change of the function from 2 to 4? Now, what are we referring to, the 2 to 4? Are those x values or y values? The 2 and the 4. those are x values. Absolutely. The x-axis, the x-axis is the independent axis, right? These are your x values. That's your independent variable. Your independent variable. So that's always what we're talking about is your input. We're talking about x, the independent variable, the input. So they're always going to be talking about inputs first. So now on your graph, go ahead and locate the coordinate that's above the 2, the coordinate that's above the 4, and that's the slope that we actually want to find. The average rate of change of the function from 2 to 4. If we wanted to, we could say that the x-axis represents time, because then we'd actually be saying something. You know, we'd be saying between time equals 2 seconds and 4 seconds, what was your average velocity? Because remember, slope is telling us an average velocity, an average rate of change. So what is the slope? You can just look at the graph and tell me. How far up do you go?
2.
2. And then how far to the right do you go? 2. So we can just go ahead and write down m equals up 2, right 2. That's 1 over 1. That's the slope. The average rate of change is 1 over 1. For every unit that you go up, you go 1 unit to the right. For the whole rest of today, we're just going to be calculating secant slopes, essentially. Secant and instantaneous tangent slopes. How about this next one? This chart shows the living wage jobs in Rochester. Where's Rochester? New York? I don't know. Could be. I mean, there's probably multiple Rochesters, to be fair. I have no idea. Well, they're saying that these are the living wage jobs. So what does that mean? This is obviously the year. Does that mean that you make $645? What is that?
How many jobs?
It's the number of jobs in Rochester that offer a living wage. So 645 people in the city of Rochester are living with enough money. Apparently, that's what they're saying. Although, I already said that wrong. It's 645 jobs per 1,000 people working age adults over a 5-year period. Okay, so what we're saying is living wage jobs in Rochester per 1,000 working age adults. Yeah, so out of 1,000 people, only 645 living wage jobs are available. Whereas look what happens over time. Good old Rochester, right? Things are looking up. They must have good politicians in that town making all of those jobs available, right? So what are we actually wanting to find? What is the average rate of change in the number of living wage jobs from 97 to 99? So we're going to go from 97 to 99. Now, which is the X and which is the Y?
The year.
The year is almost always X, and the other one is almost always Y. And if you wanted to, you can make yourself a quick little graph where we would say, let's say 1997 is the first one, and then 98, and then 99, and then 2000, and then 2001. And okay, so that was it. And then they started at 645, and they ended at 790. And so we would show something like, right? I'm not guaranteeing that that's a straight line or anything. I'm just saying, roughly speaking, is that the graph of the data? Yeah, it's the graph of the data. It's not a perfect graph by any means, but it's always nice to visualize what's happening. So what is the average rate of change in the number of living wage jobs from 97 to 99? Well, first of all, is this a coordinate?
Yes.
Is that a coordinate?
Yes.
Yeah. Now, you don't actually have to use the numbers 97 and 99. And in fact, you don't even have to do the whole slope formula, right? That could be a little more than we really need. Like if we call this our x1, y1, and this is our x2, y2, we actually have to go through that whole process of plugging up the cell in. No, we don't. We can just look. Everyone watch how I'm going to do this. You can just say, what was the change in x? This is your delta x. What was the change in x? 2, right? I'm going to use the definition of delta y over delta x, not x, y2 minus y1 over x2 minus x1. I'll just say delta y over delta x. The delta x is obviously 2. And what's the delta y? Is it 95?
Yeah.
Yeah, 95. So our slope was 95 jobs over 2 years, which reduces to what? Is it 47.5?
Yes.
Did I get that right? Okay, so see, now we can say something incredibly concrete about the city of Rochester. Over the last 5 years, from 97 to 2001, the average rate of change of living wage jobs increased by 47.5 jobs per year. And that's what you'd say. Everybody, you can do the second problem on your own, right? You're about to find the average rate of change between 99 and 2001, you can do that later. Everyone, let's move forward. Is this the next page or at the bottom? Okay, bottom. Number 3, find the average rate of change. Everyone, read that problem. Tell me what's happening in your brain right now as you read that problem. Is it fear, concern, unease? All of the above. Maybe a little bit, right? We're looking at that problem thinking, whoa, 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 what happened to the jobs in Rochester? Right? But what's always a good first thing to do? Draw a graph, right? Always, always, always. A good first thing to do is to draw a graph. So you all are required to have graphing calculators in this course. I'm going to go ahead and graph it on my good friend Desmos. So we can all look at it together. It's 9x squared minus 7. Now, you don't necessarily have to follow along on your graphing calculator right now. You can just kind of watch with the group. Well, let's go ahead and take a look. We're looking at the interval from 1 to 2. So let me make my graph look a little better. I'm going to change my y to go from 0 to, gosh, 10 maybe? 10? No, that's not good enough. I need to go much higher. 350? Oh, there we go. That's good. Everybody, can you see the window that we're talking about? Mm-hmm. So on the interval from 0 to 2, wasn't that the first one? Yeah, oh, from 1 to 2. The interval from 1 to 2. So take a look at the interval from 1 to 2. Let's go ahead and draw that. Go ahead and draw a graph. Make sure your y-axis goes up to 30. Your x-axis only needs to go to 2. Boy, I wish I had some better markers. So I'm going to do this with you. So this goes up to 30. This goes 1, 2. And our parabola is centered on the x-axis. It cuts through just before the 1. Notice I'm going to put some dots on the graph first. The parabola cuts through there. It comes down to here. And then by the time it hits 2, it's all the way up at almost 30. So 2 up to 30, there it is. And then at 1 is just up a little teeny bit, like at 2. So there we go. Can everybody see how our parabola is essentially going? So now go ahead and make your parabola. That's what you want it to look like. Folks, it doesn't have to be perfect. It doesn't have to be perfect. Because what we're about to do is just calculate a couple secant slopes. But it sure was helpful to have a picture before we started doing that. So what's the first 2 points that we want to calculate the slope between? Between 1 and 2. That is between x equals 1 and x equals 2. So find those 2 points. Here's my first one, x equals 1 and x equals 2. And what's this coordinate? And what's this coordinate? All right? Remember, once you know the x coordinate 1, what do you do with the 1? You just plug it in, right? So 1 squared is 1 times 9 is 9 minus 7 is 2. So the first coordinate is 1, 2. What would our second coordinate be? You take the 2, you plug it into the formula. So what is that? 2 squared is 4 times 9 is 36 minus 7, 29. So our second coordinate is at 2, 29. Now this is all well and good, right? All of us now can very easily calculate the slope between 1, 2, and 229. And in fact, it might even be fun if we did the delta y over delta x again. Stop thinking about y2 minus y1 so much and more about the delta y. How did our y change? It went from 2 up to 29. What was the total delta? 27. So we gained 27. And then what was the delta x from 1 to 2? So just 1. So there's our slope. It's 27 over 1. That was the average rate of change on the interval from 1 to 2. So I could draw a secant line right now. That would be the secant line slope between those 2 points. That's what we just found. Adam?
So for our test, you want us to put positive or negative, so we can clarify that.
I think it's always a good idea.
Okay.
Yeah, because we're talking about delta y. Delta y is a positive or a negative quantity. Yeah, I think that's,
Marked off if you don't.
well,
If you
as soon as you get the wrong answer because you made a mistake, you get marked off. So yeah, it's a good best practice. You see me doing it. It's not just because I'm modeling it. It's because that's how I would do it.
Okay.
Yeah, thanks, Adon. Okay, now, you notice how much work we had to do this? We had to draw a graph. We had to look up the graph, see what it looked like, draw the graph. That's good practice. But what's a different way that we could have gotten our numbers 29 and 2 and 2 and 1? I want to share with you right now, okay? That would be, in the most general form possible, everyone write this down with me. Our slope is going to be the y2 minus the y1, and then the x2 minus the x1, right? Well, what was our y2? y2, how did we calculate the y value? You took your 2 and you did what? You plugged it in? Everyone write this down. 9, 2 squared minus 7. Right, wasn't that our y value?
Mhm.
You just plug in the 2? What would our other y value be? What'd you do with the 1? You just plugged it in that formula? So that would be 9, 1 squared minus 7. Right? This might feel a little strange, but it's helpful to see the structure of what we're doing there. We really just use the formula to plug that in. And then what on bottom? That's the easy part, 2 minus 1, right? So now that we've seen that in a very formal, structured way, obviously what would you do? You would just calculate all that, right? So you'd have the 2 squared is 4, 36, and then that would be the 29, and then that would be the 19, that would be the 2, and so on. But it's helpful to see it this way, because now we want to calculate the average rate of change between 1 and b, right? Well, can you plug b into this formula? Sure. What's the answer? 9b squared minus 7. Not very exciting because you can't calculate an actual number. But let's do it this way with b and 1. What would our average rate of change be? Our first y value would be what? We're going to plug in b. And that will be some point on the graph, right? So what happens if you plug b into that formula? What do you get? 9b squared minus 1. And then the second one, well, we already know what that is because we already know what happens if you plug in 1. What's this one? 2. So that was our first value of plugging in b and then subtracting, plugging in 1. And then what's our distance between b and 1? How far apart are they? We knew the distance.
1 and b.
Well, b minus 1. B minus 1 is the distance between them. Because what's the distance between 1 and 2? 1. And how do you get that? 2 minus 1 is 1. So if you want the distance between b and 1, that distance is b minus 1. Of course, maybe that's obvious because this formula is x2 minus x1, and that's our x2 and that's our x1. So it's b minus 1. So how does the numerator simplify? We have 9b squared minus 1 minus 3.
The 1 is actually a 7.
That's a 7?
No, the 1 on the equation.
That's a 7?
No, on this one right here, on the 9b squared.
You're
minus
right, that's a 7. Thank you, gosh. You guys, thank you. Okay, so that what is that really? 9b squared minus 7 minus 2, all over b minus 1. Now some really exciting stuff is about to happen. Calculus is algebra with a lot of cancellations, okay? So on the top, what do we have? 9b squared minus 9. What can we do to the top? What can we do to 9b squared minus 9 in terms of simplifying?
Take out b.
You can take out a b. You can take out a 9. Right? Can't we take out a 9?
Yeah.
So 9 outside of b squared minus 1, all over b minus 1. Now, what can you do to b squared minus 1? This is an old factoring rule. This is the difference in two squares. And perhaps you remember that when you have a square number minus another square number, you can rewrite it as b minus 1 and b plus 1. Now that's an old factoring rule. Maybe I'll jot it down right here under my notes. So in terms of factoring, and this is something that we'll do frequently, in general, if you have a difference of squares like a squared minus b squared, the result is a minus b, a plus b. And I'll give it to you in a way you probably remember. X squared minus 25. How would you factor x squared minus 25?
X plus 5.
Yeah, x minus 5 and x plus 5, or x plus 5 and x minus 5. That's an old factoring rule. I hope that rings a bell. Because calculus is tons of algebra with a lot of canceling. So now that we have factored the numerator, what can we do?
Cancel.
Here we get to cancel the b minus 1. And our final answer is 9b plus 1. That's the slope between 1 and any value of b. What are we all dying to do? What should we plug in for b to check to see if this worked? What should we plug in for b to see if it worked? 2. Let's see. If I plug in 2, 2 plus 1 is 3 times 9 is 27. Was our first slope 27? Yeah. So it worked. So what we just did, folks, was we did the slope, the average rate of change twice. We did the average rate of change, a secant line, from 2 concrete numbers that we knew, from 1 to 2. But then we did the secant slope between one number we knew and one number we didn't know. And we came up with a general formula for what the slope is between 1 and any number in the universe. Yep. All right. I realize now that I did not give you nearly enough space for that, did I? Probably not. Yeah, that one, I should have given you more space. I'm very sorry. All right, so moving on to number 4. Number 4, does number 4 look familiar? A little bit? What does it look like? Yeah, we're getting closer and closer, right? We're calculating the slope between 2 points. So we're definitely calculating 3 and 4, then 3 and 3.5, 3 and 3.1, 3 and 3.01, 3 and 3.01. So what are we doing with the 2 points that we're finding the slope between? We're bringing them infinitely close together. This is what we did in our warm-up activity. And so that's what they're saying. For each value below, enter the number correct to 4 decimal places. Suppose an arrow is shot upward on the moon, and you shoot an arrow. With a velocity of 34 meters per second. That's the velocity at the moment you let go of the arrow. Then its height in meters after t seconds is given by this formula. So this formula is the height of the arrow. Okay, that's the height of the arrow. Find the average velocity over the given interval. So between 3 and 4 seconds, what was the velocity of the arrow on average? Notice we're not saying the instantaneous velocity of the arrow until we get down more to here, right? If you find the slope between 2 points that are infinitely close together, that's the instantaneous velocity of the arrow right there. But what we're doing is starting by looking at the average velocity between 3 and 4 seconds, between 3 and 3.5 seconds, and we're approaching the instantaneous velocity of the arrow at exactly 3 seconds. So what do we do? Now a picture would be very helpful. A picture would be very helpful, and in fact we can go ahead and draw a quick little picture, folks. I like that idea. It's going to look like that. It's an upside down parabola. I'm sure you want to see the actual picture. 34t minus 0.83t squared. 34t minus, oh, not t, x minus what? 0.84x squared?
No, 8.3.
8.3?
Well,
0.83.
0.83.
Oh, okay, 0.83. Oh, I was a little off in my drawing. What does it really look like? It starts at the origin. Oh, and that should make sense, right? Because where are we standing? We're standing on the surface of the moon. We shoot the arrow, so it's going to go up and then come back down. So that's our picture. And notice between how many seconds are we interested in? 3 and 4. So where is that on the graph? Right around here. Right? We're talking about the speed of the arrow as it is what? Going up. And as the arrow is going up, what's happening to its velocity? It starts off fast, then it slows down and stops, and then it speeds up again as it comes down. So around 3 seconds, it's still going pretty fast, but it is nevertheless going slower at 3 seconds than it was at 0 seconds. Okay? So now that we have our nice little picture of what's happening, a picture is always helpful. And we already found out t equals 3 is on. So we know What kind of slope should we end up with? Positive, for sure, between 3 and 4 at first. So we're calculating a secant slope between 3 and 4. And folks, we're going to utilize the sit over there with the b, but I'm going to give you the general formula. Okay? Here's what our general formula would look like. The slope would be, if you wanted to go between any 2 points, A and B, it would be f evaluated at B minus f evaluated at A. Oh, I should be using h. Since we're talking about the h function, let me use h. H evaluated at B minus h evaluated at A all over B minus A. That might look crazy at first. Let me draw another picture. If we have this parabola and my first point is A and my second point is B, what's the y value when x is A? How do you calculate the y value? You plug A into the formula, and the formula is h of a variable. So the y value is h of A. And then if you want, you plug in B. When you plug B into this, it's h of B equals all that. So that would be the y value, h of B. Okay? So then when we're looking at delta y, what's the delta y? H of B minus h of I, h of A. That'll tell you how much vertically you've shifted. And then what's your delta x? B minus A. So again, our slope, I could have put that first. M equals the delta y over the delta x is the function evaluated at B minus the function evaluated at A, and then all over B minus A. But fortunately, we're using real numbers. So what is this actually going to look like? H of 4 minus h of 3 all over 4 minus 3. That is going to tell us the slope, the secant slope. And therein lies the good news about the use of calculators in this class. You don't have to sit there and do all sorts of PEMDAS and work this out by hand. What you're all going to do is simply take this formula and plug 4 into it. So on your calculator, 34 times 4 minus 0.83 parenthesis 4 squared, and whammo, it just tells me the answer. So that's what everyone can be doing right now, is take out your calculator and type in 34 times 4 minus 0.83 times 4 squared, and the first value is 122.72. Now, it's so important that you do this. I have memories last year of a couple students who just watched me do all this, and then later on they went home and they said, I have no idea how to do this.
Minus 4? I mean minus?
Yeah, then minus the h of 3.
Okay.
So then what you can do is hit second entry. It pulls back up everything you just typed in, but you just change all the 4s to 3s. Very convenient. And that number is 94.53. Of course, the bottom is easy. 4 minus 3 is 1. Now, folks, I'm throwing a lot of new notation at you today. Like, for instance, m equals delta y over delta x. Maybe you've never used delta y over delta x before. And then h of b minus h of a over b minus a. I mean, this might look crazy at first. But remember, ultimately, what are we doing? Just the slope formula. Right? We're just doing the slope formula. And so we're calculating our y coordinates. We're calculating our x coordinates. We plug it all in. And what did we get? Was it 28.19?
Yeah.
Okay. Now, what does that mean? Feet per second, right? Oh, meters. Meters per second. It was height in meters. Is that the instantaneous velocity? No, that was the average velocity between 3 and 4 seconds. So on average, between 3 to 4 seconds, the arrow is flying an average of 28.19 meters per second. So let's try that one more time as a group. I'm going to skip down to this interval from 3 to 3.1. And we can set it up the exact same way. I want to know the slope, which is my delta y over my delta x. I can use my formula that it's always going to be the height function evaluated at the second coordinate, 3.1, minus the height function evaluated at 3, divided by 3.1 minus 3. And then you use your calculator to type all that in. In fact, you should still have the formula somewhere in your calculator that you can just go back and type in 3.1. Or you can just type the whole thing over again. It really doesn't matter. It's going to be 34 times 3.1 minus 0.83 parenthesis 3.1 1 squared. Make sure you do it right, not wrong. I just did it wrong. There we go. And my first value was 97.4237 minus something. Okay, I'm going to take a pause and just come around and help you all with your calculators. So let me know if you need assistance getting all this in your calculator. Did it work? Okay. Is it working out? Okay, so we did that.
Yeah, I got it.
Yeah. You should. So when I calculated, what number are we doing? The 3.1? What is this? So I did a 3.1 and then minus 1. 3.1 squared. Parentheses is
34, right?
there we go.
And then you can second entry,
Pulls it all back up again.
Why squared is that?
Change it to 7.0. Which is
Like, you forgot to do minus.
yeah, 3. Well, no, yeah, just 3.1 and 3. So now I have both of my values.
Minus.
Okay, this is kind of tough to do on a calculator like that. So I can start bringing you a spare calculator until you get one, but this is a requirement, of course. So how about?
Mr. G did it wrong.
No.
Oh, okay, but it's, okay, well, I'll bring you a calculator and take it. Yeah.
You put 3.1 is 3.94.
I'm doing the one on 3.1. Yeah, that's okay, you're calculating a
No,
perfect.
3, and you put it
Oh, okay.
Okay. Alexa, what's your calculator?
I forgot it.
Oh, no, okay, well,
I get it.
okay, I'm gonna bring some extra calculators next time so everyone has one. Did he show you how to do it? Was it?
Yeah.
Okay, yeah, you got it, 97.7. Anna, how's it going? Bring it? Oh, good, yeah, it's working out.
Because
Great.
like first, this.
Okay, I'm gonna go ahead and
And like,
calculate this now.
I have to look at the 3.
So for this particular problem, I was doing 3.1 to 3. I did that, 94.53, and it's gonna be 3.1 minus 3. And that gives us that the average, 97.4237 minus 94.53. The average was 2.8937 divided by 0.1, which is 28.937. Now folks, what do you notice about the first value of speed and now this value of speed? What happened to it? The value went up, right? Now, does that make sense? After all, here we were saying the average velocity from 3 to 4 seconds. Look again at our arrow. At 3 seconds, our arrow is still going mighty fast. But by 4 seconds, hasn't it slowed down a little? So at 4 seconds, it's going slower than it was at 3 seconds. So if we take the average from 3 to 4, the average is being slowed down by the later number. Whereas the closer we get to just calculating the speed at 3, what would we expect the velocity to be? Faster, right? Because it's faster in the beginning than it is at the end. So this makes sense that as we make this window closer and closer to just 3, the velocity is going to be highest at 3 alone. Okay, well, that's as far as we're going to go with this. Anyone just want to take a guess? What do you think the speed is at exactly 3 seconds? What do you think we're approaching? Anyone want to take a guess?
30.
Maybe 30, maybe 29, maybe something like that. It's not going to keep getting infinitely, right? You know, it's going to level off at the actual speed of the velocity of the arrow at 3 seconds. Okay, I know I'm running out of time, but let's go ahead and see if I can at least get you started on number 5. Folks, I didn't quite finish today. And that's because we did that nice long introduction to calculus at the beginning of the hour. So what we're going to do is we're just going to let this class period flow over onto next Tuesday, and we'll finish section 2.1 on Tuesday of next week, because there's still a lot of good material in here that I want to go over with you. And therefore, I'm going to extend the due date of the Math AS 2.1 until the following week. Okay, so everyone can just relax and know that you don't have to go home and figure this out on your own. What we don't finish today, I will finish on Tuesday. Because it just so happens that section 2.2 is fairly short. So we can easily do this. Okay, well, let's try this one more time, folks. A ball is thrown into the air by a baby alien, that's obvious, on a planet in the system of Alpha Centauri. Why not? With a blanky blank. Velocity of what?
35 feet per second.
Yeah, 35 feet per second. Yeah, I can do that. Its height in feet after t seconds is given. There's our function. Then what?
Find the average
Velocity for the
for
time.
the time.
Oh yeah, find the average. Yeah, so we're finding the average velocity again, right? So the key thing is that our function is what? The function is
Y equals 35t.
35t
Minus G squared.
well, t squared. Okay, great. So that's our function. So once again, now, notice, did they give us an interval now? They didn't literally give us two values, did they? They just said, let the interval be 0.01 seconds long. Remember, that's how far apart the 2 points are. They're saying calculate the slope between 2 points that are 0.01 seconds apart, calculate the slope between 2 points that are 0.005 units apart, calculate the slope between 2 points that are 0.002 units apart, and then calculate the slope between 2 units that are 0.001 units apart. So what are our points doing? They're getting closer and closer together. Because in the long run, if you keep doing this process, you're going to find the instantaneous velocity at exactly t equals 1. So when does our time period begin? T equals 1, right? So what's our first interval? We start at 1 second, and then we go 0.01 seconds to the right. So when does the interval end? 1.01. Or that's it. They just gave us the information in a different way, didn't they? So now they want to find the average secant rate of change between t equals 1 and t equals 1.01. And what will that function look like? M is the delta y over the delta x. And that's going to be f of 1.01 minus f of 1 all over 1.01 minus 1. That's what the formula looks like. We're doing the y value evaluated at the end of the interval minus the y value evaluated at the beginning of the interval. Again, if you were to draw a picture, this will help to make more sense. Again, our diagram looks like this. We're starting at 1 second, and we're choosing another point just a little bit to the right of it. And remember, if you have 1.1, 1 and 1.1, isn't it? No, 1.01. How do you calculate a y value? How do you calculate a y value? You plug it into the function, right? That's always how you calculate a y value. So this value would be f of 1, and this value would be f of 1.01. Now you probably all noticed that I switched from y to f of x. Why did I switch from y to f of x? They both mean the same thing. You know, y equals and f of x equals, they mean the same thing. But f of x provides us a really handy-dandy way to just write it down, knowing that we're going to plug 1 into the function, and we're going to plug 1.01 into the function. So, sure enough, if this coordinate is 1.01 comma f of 1.01, and this coordinate is 1 comma f of 1, then we're just doing the slope formula, right? y2 minus y1 over x2 minus x1. And that's exactly what we've written down here. So then, how do you finish this problem? Use your calculator. Yeah, you just use your calculator and plug it in. So really, this is very much like the previous problem. Okay, well, I guess that's as far as we can make it today. Oh man, this is such good material. I wish. Can you guys just stay? Stay for half an hour. Come on, guys. It's free. I won't even charge you. No. Just stay and we'll do more. It'd be fun.
Are you gonna go to my other class?
Oh yeah, no, I can't go to the other class. Yeah, well, not bad. We got halfway through. So on Tuesday, we'll finish 2.1, then do 2.2, and I'll extend your homework. But when are you going to start the mathematics homework? Today. Start it today. Immediately go on there and try it out. Always start the same day, because it makes you feel good about yourself. You're like, yeah, that's right. I already started the homework. It feels good. So wait, you guys really aren't staying? 20 minutes. 15 minutes. Let h approach 0. 0.0001 minutes.